Okay, ladies and gentlemen, it's time. 1 o'clock. Welcome back. Hopefully everybody had a full and satisfying lunch. We have an exciting afternoon for you. First up is going to be the technologies and capabilities for a NEO, a human mission to a NEO. And so we have Barbara Wilson, who led that group, and we also have Eileen Stansberry and Chris Moore, who are the respective facilitators. So without further ado, we'll let you go ahead and do your outbrief, and then we'll open it up. Again, for today's format, we'll do 15 minutes of brief, 15 minutes of Q&A, then we'll step to the next group, and we have 3 groups here from 1 to 2:30.
Now that I know where to point this. Okay, well, we had a really lively 2-hour-long discussion today in our group, and I'll state from the beginning that what is up on the charts is a little less than half of what went on in the group at best, but we did try to capture what we seemed to, what the individuals in the group found most important to try to capture. The desired outcome from this group was the identification first of the capability gaps that you would need to close in order to meet the types of objectives that we discussed yesterday at the workshop for a human NEO mission, and then to individually rank those capability gaps as to the importance of needing technology development in order to close them before it would be reasonable to fly the mission. And then, after having identified which ones we thought were most important individually, then we went and looked at what kind of technologies and technology development were options to, in fact, close some of those gaps. So the questions followed along the same lines, but I want to make a very clear point so that it's on the record that the only part of the mission that we, in fact, considered was the on-site part of the mission. Obviously, the launch, the getting there, the on-site part, the getting back, getting re-entry through Earth's atmosphere, et cetera, all have technical challenges. And in many cases, some of our panel members felt possibly more important. Yes, than the, I thought it was my watch, it's not. I'm done already. More important than the ones that we actually talked about on site. But we had decided that that was going to be the focus for this activity. And in particular, just that you have to focus on the on-site part, which is NEO-specific. And we were very hopeful that the other parts will not be ignored in the following technology analysis for the future. So, from the objectives that came out yesterday and the discussions in yesterday, and also a precursor question that I sent out to our group asking about where they saw probably the primary challenges for operating on or near a near-Earth object, we ended up using a set of 4 categories to try to structure our discussion. And the idea was to capture areas that are relatively independent, so that it's pretty clear what goes where in the categories, but that also both span the space of key technology or key capability gaps, and stimulate discussion in all the important areas so that we're trying not to leave any important areas out. So our categories were, first of all, what we call prox ops, which is associated with all of the operations near or on or under the surface of the near-Earth asteroid. The second being the question of actually the characterization of the target, both surface, material, internal structure, et cetera, and the handling of samples and the gathering of samples and handling of samples to maintain their pristine characteristics. The third one we called on your own, or on our own, if you're the one there, with the idea that you are far from any repair service, you don't have a logistics train coming up easily to help you out, and so we were looking at things like reliability, mission system autonomy, and robustness for how to operate at this distant place away from ground support. The fourth one we pulled out just to make sure that we put an appropriate emphasis on human systems. So even though life support obviously has the same issues of robustness, mission autonomy, reliability, et cetera, we actually included life support out in the human systems that also dealt with all of the aspects of human health and performance. We had a category for other. As you can see, we did actually get one item that didn't fit in with the rest of them, but by and large, these categories seemed to work pretty well for our group, and had a pretty uniform, a good set of stickies that went up on the board that are listed just the number on the right. Those have not pulled duplicates, but the idea was that there was a lot of action and interest in all of these groups. We also, just as a cross-cutting comment, that reliability, autonomy, and smart systems seem to be recurring themes across many of the discussions. So I will now move through each of these areas. And what's shown here on the left-hand side is when we each ranked how we saw the importance of these gaps. We first did it at our own tables, and then afterwards we also did it scoring the other tables after we heard what the other tables' thinking had been, so that we actually ended up with multiple rounds of scoring. And looking at that, it turns out then, like for the first one, that there were we had people, you could score 3 points for your top one, 2 points for your next one, and 1 point for the one most important after that. And so that just is a count of the scores that came in from individuals. So among the top 4, in the proximity operations area, first is the actual touchy part of the interaction with the NEO from an EVA perspective or robotics, and anchoring yourself to be able to get around and touch and interact with any point on the surface. So in terms of technology development options, many of these are still, we didn't have a chance to talk these through in great detail, but we just looked at types of areas that should be considered for potential development. And they included things like jetpacks for getting around, other ways of anchoring and or tethering yourself to the surface, a suit lock for a fast ingress, looking at teleoperation of robots, and the whole human-robotic interaction was a big part of the discussion also, and how you operate with both humans and robotic systems most effectively and efficiently. We have the whole suit and robotic systems in general, the MMSEV, the man in a can, the working around the surface in a system, again with the suit locks potentially. Free flying, some ideas on free flying lighting and cameras to support the activities. A clean suit in terms of, this came up a number of times, both with the exhausts or effluents, et cetera, from all of our human systems and or spacecraft systems, that we don't want to contaminate the surface that we are trying to look at. So we have to be concerned about approaches that look at keeping from measuring ourselves when we get there. There were also concerns about dust mitigation, electrostatic issues, and tools for EVA, and although this is captured elsewhere also, the idea if you're going to, in fact, be trying to anchor and put instruments down, et cetera, you need to understand the local subsurface characteristics for being able to work at that location on the NEO. Coming in at number 5 was the spacecraft part of this, where you are in the vicinity, but presumably this is the part where you're not actually touching or interacting with the surface, but you're hanging around in station keeping, rendezvous, and there's a fair amount of gaps in that area that could use technology development, which includes the control systems for working in this environment with non-uniform gravitational fields. Things were rotating. It's a very complex and unknown problem in advance when you get there. We have sensors for understanding your situational awareness and your position determination, which could be radar, LiDAR, other. You need to be fuel efficient if you're going to be flying around and accessing all these different places and or station keeping. You have to be able to do this without using tremendous amounts of fuel because you have to bring it all with you, of course. Then there's an aspect associated with I talked before about plume impingement in terms of contamination, and also the whole idea of the information systems, the smarts, for modeling and algorithm, et cetera, for terrain relative navigation, because you need to use the body that you're actually trying to stay near to for your prox ops. In the characterization area, While we had a lot of identified capability gaps, when we came around to voting, most of the individuals actually found other areas being more important in terms of the top 4 or so, but these two both did come in with notable scores nevertheless, that a number of people found them still very compelling. And the first is associated with the actual sampling and prospecting, so it's acquiring the samples, drilling, coring, getting the samples from the subsurface, local anchoring, as I mentioned before, so that you could in fact apply forces to do this drilling and coring or other ways of interacting with the interface. And therefore knowing what's underneath there locally, but also, of course, there's the need to want to try to understand whether indeed you're talking about a rubble pile or a big rock or a loose conglomeration, et cetera. So you need approaches and instrumentation for subsurface characterization, which still has some challenges also. We also talked about the idea of maintaining the sample pristine after you pull it out, so you have both the encapsulation for return as well as making sure you don't lose your volatiles, et cetera, in the samples. We talked briefly about planetary protection. I think in general, from a asteroid perspective, this isn't a major issue. There's the forward contamination that we did talk about previously. Okay. And then, of course, the approaches for measuring things so that you make sure that you, in fact, are selecting your best samples. So the triage aspect of being able to select the best samples. So you need activities, you need to be selecting where you pull the samples from in an intelligent manner. Actually, then doing some of the science you want to do while you're actually there, that you need onboard laboratory capability, which therefore requires that this instrumentation be much smaller than the labs back home in our own laboratories here on the ground. So miniature instruments, expert systems to try to speed up the analysis and understand what it is that you're trying to look at and decide what you're going to bring back. A good bandwidth of communication for being able to send results that you get back and have additional support from the ground. And as it said, we need clean containment of those samples. So there's a strong sense here of focus on subsurface and interior structure and on on-site analysis. In the on-your-own area category, the first one is associated with the autonomy, the ability to solve stuff, to do stuff by the crew that is there, mostly because of the light time issues. You've got to make decisions based on the full impact of the situational awareness that you are the only ones that have that. And so there were a number of activities associated with the system autonomy and automated planning and mission operations, including designing for reconfigurability and adaptability in your systems, artificial intelligence, the health monitoring, understanding the status of your systems, and certainly onboard mission planning as opposed to canned sequences. You're going to have to redo and understand in a flexible way, how you're responding to the environment and what you're going to do next. And likewise, just-in-time training, because you've got a new set of things that you're going to deal with that you couldn't have planned for exactly on the ground. Also here, but seen as by fewer of our members as highly critical, was the question of reliability and repair, although this is especially for a feed-forward perspective, that for longer missions downstream, the system reliability is going to be key. You don't have service coming in to help you out. You don't have a logistics train, and you have to take everything with you. So being able to, in fact, have functional redundancy, common components that you can share so that you don't have to have a spare part for everything. You can have a few that handle and that can support a number of different systems. A robust ecosystem, which is both a function of the lack of the reliability, so you don't have things breaking that you've got to replace, and also that you aren't having to bring up as much in the way of consumable filters, et cetera, in the system to be able to have a system that will continue to function while you are there far away from home. To some degree, the question of whether you can in fact do parts manufacturing on demand, on site, and self-repair, and fundamentally that you're designing in fact for sustainability and reliability. And we also have put in place test programs to understand the full reliability of our systems. So some of the key points that came out of this discussion were the autonomy and reliability are key, that we have to think about the architecture in terms of logistics and sparing, and we also, as I didn't mention in passing, but I should have on the list there, but it's small to read from here to remember everything that's on this list. The fault detection, isolation, and recovery, and the whole architecture for that approach as to how to do that when you in fact can't have your back room full of all of the experts, and you have to have a lot more autonomy on board that deals with faults that will happen and how you recover from them. And then the final system in the human systems arena, both of these were in fact the top two out of our entire discussion. And the first is in terms of radiation protection and warning, to both detection and warning of and understanding how much dosage you've had, prediction, models, shielding obviously, and shielding design and approaches that in fact can be done with low enough mass that you can effectively bring this with you. And the potential for pharmaceutical countermeasures, and understanding what each crew member has been exposed to. But likewise also in general for rad-hard systems, and to shield the whole vehicle as well as the human side. Also the high reliability of human life support. So this is the counterpart of the rest of the systems on board for high reliability. Here for the human side, it was thought to be the highest category that we looked at. And it is both from closure for air and water of the life support system, miniaturization of the system, and the low consumables footprint that was measured with respect to other things also, that you have to have a system that you don't have to bring tons and tons of the replacement parts up there to keep things running. We noted as a group that there is a lot of good work ongoing under HRP, and suggested that would be worthwhile continuing. I guess I thought I'd remove this page. I apparently didn't. But wanted to see what I had as a comment that I'd written here. Just as a comment then in final, that we did not look at the other parts of the mission. There are a whole set of, again I repeat, a whole set of capabilities and technologies that are needed associated with other phases of the mission. This is just the on-site portion. But the sense that the human system side was a very important piece, in that we had thought about it at the beginning of thinking about the capabilities needed, from a sense that we do deep space missions already, but what's different about the fact that you now have humans on board? Or likewise, we do humans in low Earth orbit and have done to the moon. What's different about taking humans farther than where we've taken them before? So those were some of our guiding thoughts to make sure we were trying to capture the range of activities. That's what we have.
Okay, wonderful job. Now we'll open it up for questions for the next 10 minutes. And I remind you, I guess we didn't hear that the first time. We'll now open it up for questions for the next 10 minutes. And thank you, Clive. We would like folks to use the microphone so that the web audience can hear loud and clear.
Yeah, I turned it off on purpose, all right.
Sorry, can't hear you. Was you, Clive?
Yeah, Clive Neal, University of Notre Dame, Midwest boy. Just a question with regards to the technology session there. Did anything come up with regards to the feed-forward aspect, making the technology applicable to multiple destinations rather than just being for NEO? So if the ultimate goal is to go to Mars, is there going to be flexibility in some of these systems? And did you discuss what would need to be unique, and then what could be carried on to other destinations?
I'll make a comment first, but I will leave the opportunity for either of the facilitators to respond to, because by definition I heard less than, or at most half of either one of the conversations at the two tables. We didn't talk specifically about synergy at all, since there's another panel that was specifically addressing that. The only aspect that I was aware of that we talked about that was feed forward really is the sense that all of these activities are taking place in deep space, and so the whole question of reliability, repair, robustness, autonomy, autonomy are all things that obviously carry forward into any mission and are going to be even more important for missions that are longer than this one.
Yeah, in particular, the table that I was at had more discussion on mission duration and how that relates to the technologies required, rather than anything that was specifically a destination-dependent issue, because the synergies group was more or less assumed to be able to be addressing that. But there was considerable discussion on both the mission duration and how that affects what you do, and not limiting our technologies for being specifically a 6-month NEO mission, and that's it. So there was some discussion of feed forward, but not necessarily how it specifically manifested itself.
Okay, thank you.
One of the key level 0 objectives that our group came up with yesterday was the establishment of an affordable transportation architecture. And so I'm wondering, did you guys, I didn't see any technologies relevant to in-space propulsion, for instance, that could reduce the cost of the mission.
Right.
Well, yeah, actually, my group talked about that in addition to the instructions that we were given, is that we had decided to, because we only had 2 hours, to only focus our work on once you got into the vicinity of the NEO. So how you got there was assumed to be a piece of work that needed to be done by someone else. And so the in-space propulsion, as it related to getting from Earth-Moon vicinity to a NEO vicinity, was something we chose not to address at my table.
Yeah, excuse me. Yeah, that's right. We just assumed that there would be some in-space propulsion system available. The only aspect we talked about was maybe we could use the electric propulsion system once it's arrived at the NEO to supply power for surface operations. So maybe we could beam power down to the surface that was generated by the solar rays on the SEP system.
Okay, great. As long as you guys recognize that there's a big technology gap there, too. That's
Right, yeah.
Mike Sander, JPL. So one of the things you touched on was this notion of logistics. And I'm just wondering whether there were any specifics with respect to, and it could be judged as really an architectural issue as well, making sure that there wasn't, one particular card designed for every single function, but rather taking a look at the architecture of the system design to minimize the number of different designs that were incorporated into the system, so that there would be reuse or possible, interchange of functionality from one system or another. I mean, that's a fairly profound thing that we collectively in the business haven't done a very good job on.
Yeah, my table had a fairly lengthy and exhaustive discussion on that, because it came up a couple of times. It came up in terms of having dissimilar redundancy of any one particular system, but also in the suite of systems that are required for spaceflight in general. You would want to, we talked about multiple independent systems, but that have some level of common components that are interchangeable, so that you can, instead of doing large ORU pull out, push in kind of methodology, that you can actually just swap boards and think about your logistics train as a philosophy of sparing, a philosophy of architecture, and a philosophy of logistics, and that those things have to be related.
Since you focused on just your time at the NEO, can you elaborate on how you got to the need for closed-loop life support? Because we did habitat studies for the moon, and kind of 30 days was a break point.
It was because of the assumed mission duration and the feed-forward aspects of the mission. We didn't assume only the time that you were at the NEO, but we did not describe heavy lift launch vehicles and the spacecraft that gets you from Earth-Moon vicinity to NEO vicinity, even though we know that those have to exist, because those are sufficiently complex to deserve their own independent study.
Okay, that makes sense. Thank you.
I got a piggyback question on that one, if you will. So essentially, in looking at the closed loop versus the robustness or reliability, was one deemed to be a higher fidelity factor, or you know, you mentioned both. Was one more of a driver?
I think reliability was more of a driver, given the mission duration, the amount of consumables that we'd have to carry with us was, you know, relatively small. If we go to longer duration missions, closed loop becomes more important, but it's essential that we have reliable systems to keep the crew alive.
Okay, and one follow-on question is, you talked about you know, drilling or injection type kinetic attachment. Did you look at anything non-kinetic, like nets, blankets, barges, adhesives, freezing, crampons, that type?
We didn't have a lengthy discussion. We're all aware, I think, of a variety of options, and I think the sense was that those options need to be looked at and understood. Which ones may work for which type of body? I think we were real clear that in many cases there are approaches that are thought to be relatively well in hand for anchoring, but which one you would want to use would depend very much on the nature of the body. And so the understanding was to both to look at things that could work for a variety of ranges, but also to decide which to be ready for any of them was what was important.
Yeah, and we definitely, when we categorized things, it was, well, is there a suite of solutions that we know exist and all we have to do is do the design, development, and test, not necessarily create a new kind of thing? And so most of those items were bucketed in the do some design, development, test on a wide variety of techniques rather than create a new technique from whole cloth.
Very good. Thank you very much. I'd like to say thanks a lot to this panel, and we'll bring up the next one, which is the concept of operations with Doug Craig and his team of facilitators.
All right, thank you, John. Before we get into the presentation, I just wanted to say that we had a lot of good conversations, and trying to pack the discussions of concept of operations for a mission to a NEO in a couple hours was tough. If we had a little bit more time, we could have probably gone a lot further and maybe even made some videos for you, John, but we didn't have the opportunity to do that. But we did come up with some really good ideas, as well as some issues for future analysis. So with that, we started with the day one results, as Marguerite had briefed out this morning. And then looking at that, we wanted to figure out what were the mission operations, concept of operations, and how should the humans interact with the NEOs. And what we decided to do was break it up into phases, the mission phases. We wanted to focus on the NEO, you know, what you do at the NEO phase first. But we also knew that you had time both in transit to and from the NEO that we could take advantage of, and in fact we should take advantage of. So we wanted to include that as well as the low Earth orbit and preparation, and we took a stab at all of those. And then what you'll see is we put the presentation together into the more temporal aspect of going from LEO and then transit to NEO and therefore. But you'll see we focused a lot more at the NEO. So the concept of operations for at low Earth orbit, we figured this is where you do the assembly and checkout of the exploration systems. And some of the systems that we got that were required at the NEO was a core module, which had your power, logistics, the ECLIS system. Kind of, we call it, you'll see in some other charts, like the mothership, with that and the propulsion stages. We looked at having 1 to 2 excursion vehicles, or space exploration vehicles. You saw the SEV. And then some return vehicles. You want the return vehicles as part of the mothership so that you can return safely. And then I'll get into this on the next chart, but we really looked at the Advanced Recon Probe, and this was brought up in the robotic precursors. So while we're going to get a lot of good information from the robotic precursors, we may have a launch slip. And so if you did, we wanted to make sure that if we slipped a launch for one NEO, that we could probably we would end up having an alternative NEO to go to. And so we would want to be able to send an advanced recon probe out to get information to bring back to us so that we could do future planning. And then also we get into provisioning, basically getting the logistics up there, and as well as the humans. So now outbound to the NEO, basically the operations, I talked about this probe for advanced recon. You want to send it out there. It's got to be simple. It's got to be small. Whether it stops at the NEO or just keeps going by after, it depends on we'd have to do some analysis on it. But we'd like to have it out there weeks to months prior to the crew so that we could get the information back to identify the characteristics, both the physical characteristics of the NEO, the size, the spin, the composition, maybe some local features. And like I said, this allows for the target for the NEO modifications if we have a launch contingency issue. The other thing that came out was we had a lot of time during the in-flight mission, and we'd like to keep the proficiency up and make sure that the systems are being tested, so we do a lot of in-flight training. One of the ideas was to have a simulated NEO surface as part of the ships going out, and then what you could do is you could take your excursion vehicles and practice the NEO operations, the rendezvous and docking, practice your EVAs. You need your EVAs for contingency as well. So we have that. Another idea was actually to do some simulations, to have onboard simulations that you could do in-flight training with as well. And then once you got the information back from the recon probe, you would refine the flight plans prior to the arrival to the NEO, and then you would incorporate that into the training and the simulation as well. The other important part is systems monitoring, and you're going to see this throughout all phases. One of the objectives, of course, is to feed forward to other destinations, and so it's important to monitor the systems, not only for just the failures, but also just the performance, so you can have that information for future missions. And then while we're out there, we'd have time to be able to do other opportunistic research, such as microgravity, biological research, look in variable gravity or radiation monitoring, do psychological or physiological research while we're on the mission. And one of the things that we think is important is to keep the crew engaged and during the mission, especially the long duration outbound flight. It's important to keep them busy so that they continue to be motivated. It's for psychological factors. So the other thing, talking about when you go out to a NEO, you can have the outbound leg, the long duration, and with the return, the short duration, or vice versa. And we got into a conversation about that. What would be better? On the one hand, if you have the outbound short duration, then the crew is more fresh when they get to the NEO. And then when they're returning, they can do things like sample triage. But our group thought that the most important thing would be to have a long duration leg up front of the outbound so that they could do the training and get ready for it. Plus, from a safety standpoint, you have a safer return coming back from the NEO. So now we get to at the NEO, and these that we put a lot of ideas up, and they kind of gravitated towards one of four areas. Basically, operations involving human spacecraft, or EVA Ops, Science Ops, and Robotic Ops, and I'll get into that, each one of those here coming up. So, human spacecraft operations, the first thing you would do once you get to the NEO, you would do far and near field surveys, obtaining the situational awareness, ground truthing the information you got from the precursor missions and the robotic probe, looking at the hazard characteristics, and then make sure that you could tweak your operational plans as required. And you also do the resource assessment and making sure that you accurately predicted or picked the sites of interest that you wanted to go to at the NEO. Then the next phase of operations would be the orbit insertion and station keeping of the stack, if you would. And one of the things that we thought was important that the stack stay off of the NEO surface just due to safety factors. And so we basically came up with the idea of having some sort of excursion or exploration vehicle that would go from the mothership down to the NEO, and then the astronauts would use that for their EVA activities. The analogy was given that think about when you're exploring the Titanic. You know, you don't have the ship up on the surface and then just send the divers down. You actually have an excursion robotic craft to go down to the surface, and if you could have divers, then you would have them go out of that ship rather than the long traverse from the EVA standpoint. The exploration vehicle operations then would go down and somehow rendezvous and dock with the NEO if appropriate. We came up with some ideas. First off, you'd want to anchor somehow, and there was a discussion, should you anchor or not? And during we had some debate about that, whether or not you just want it free flying or you want to anchor. And after the long discussion, it's determined that the best thing to do would be to anchor there. But if you couldn't do that, then you would basically station keep doing free flying. I looked at different things like laying a cable grid for translation of the system. So basically, you could anchor several points and have the excursion vehicle translate on the grid. So that was one of the concepts that came up. Another thing that we need to look at is we want to make sure we don't kick up dust too much, and so that's going to be a big factor in this, because basically if you go there and the first thing you do is you pick up a cloud of dust, and with the microgravity there, you could end up having a dust cloud for the 14 days you're there, and then that kind of messes up your operation. So we need to take that into account. Once again, I said we monitor the spacecraft system's performance, and then you'd have the return back to the mothership when you were done exploring with the NEO. So the EVA Ops, so once the excursion vehicle or exploration vehicle is down to the NEO, the astronaut would get out using like a suit port idea to EVA to the surface. We thought it was very important that the astronaut is either fixed to the NEO or to the exploration vehicle, so that they, quite frankly, didn't float away, and it's also for other safety reasons. One of the things that we were looking at doing is some sort of translation system to help move the astronaut around, and you could either do it like we do on station with a robotic arm and have the robotic arm move the astronaut to different sites of the NEO. Or we could have the excursion lines, where we laid out excursion lines across the NEO, and then the EVA astronaut going EVA would attach himself to the excursion lines, and then we could have a cable grid, which is pretty similar. Now, one of the other discussions we had was how many crew is required for this, and we were thinking that from a safety standpoint, the minimum EVA team would be 2, and we'd always want to have at least one person in another vehicle for rescue purposes. And so we were debating whether the crew size should be 3 or 4, but it's definitely more than 2. and that is to do the IVA monitoring, not only for rescuing, but it also enables a little bit better situational awareness if you have someone standing off and being able to look and monitor the big picture, if you would, while the EVA team is out. For Science Ops, one of the things that we came up with was that basically we should have the EVA crew do the majority of the science tasks, but you'd have the robotic assistance. So for instance, in the core sampling or deep drilling, you'd have the astronaut go out there and identify the spot to drill and help set up the drilling system, but then you may leave that system there to do the drilling while the astronaut does something. If it takes 5 to 7 hours to drill a core sample, it's not the best use of the astronaut's time, so they could go off and do other things. Other science ops were setting up the surveys for seismic research, sample collection, and got into a little bit of discussion on this of, do you just sample small samples, or can you look at somehow accruing a bulk sample and then using that bulk sample as a way, what you do is you'd analyze that on the return to Earth phase of the mission. Also looking at ISRU demos, not only do they for ISRU, but also for the characterization of the chemicals and volatiles on the NEO. The other thing that we would have the EVA crew do is deploying and placement of packages. We talked about the seismic sensors or the tracking devices to validate your tracking models for the NEOs, as well as any orbital modification techniques that we were looking at, whether they be the low impulse or the detonations, if you would. So the crew would do that. But we'd also have some robotic operations prior to the EVA, or both prior to the EVA, during and after the EVA. We're looking at having some sort of situational awareness capability using a free-flying robotic system that could give people a better vantage point of what was going on. Looked at, like I was talking about, autonomous drilling, and then you might want to leave some ISRU equipment behind to let it continue to run to build up testing time for it while you leave. And so we'd also looking at leaving behind the robotic assets, something like the exploration vehicle, if you could, so they could continue teleoperation and communications, as well as you could use it for public engagement. So return to Earth, I kind of mentioned this, but basically we have a lot of time going back to Earth, and we thought the most valuable use of the time for the astronauts while at the NEO is collecting the samples, and then you would take the samples back and then you would high grade them and curate the samples on the return. You could also continue to operate and monitor the systems that were left behind, and as well as looking at planetary defense experiments such as a NEO impactor, and also continue to monitor the crew's psychological and physiological activities. So that is it. Thank you.
Excellent job. You covered the full spectrum of the ConOps phases there. So we'll open it up. Again, we've got Mike Gernhardt and we've got John Connolly here as well, who helped as the facilitator. So first up.
Yeah, David Morrison here. You seem to be satisfied with having the robotic precursor launched in the same opportunity and just got there a few weeks before, which seems a little different from some of the other assumptions. Did you talk about that much?
We talked a little bit about it, but not into much detail. But the idea, though, would be that the robotic precursor would provide us with more information on the number of the different types of NEOs and give us that information that we could then use for this robotic, for the advanced probe, if you would.
So obviously we'd like to have a precursor of the exact asteroid that we're going to and have all of that information. But the notion here is if you slipped your launch and you ended up going to a secondary target, this provides you a way to get some insight to refine your flight plan on the way out.
In the Jerry Sanders, Johnson Space Center, in our synergy group, we talked a little bit about EVAs. And one of the things that came up in our discussion was the fact that because of the dust and kicking up, plume impingement and stuff, one of the approaches might be that we would do most things with robotic assets near real time with the astronauts there, and that the astronauts are used for contingency or problem solving aspects. I saw in your charts almost the opposite, where the bulk of the activities were EVA related. And so I just wanted to throw out the pros and cons and have you guys respond to that.
I'll start. Jerry, we had that same conversation in our group. Our thought was that the reason we're sending humans to a NEO is to put scientific hands and minds as close to the subject matter as we can. And so we tended to go more towards the idea that scientists in EVA, doing EVAs are really what you're there for. So we tended to load everything that way rather than robotics. Robotics certainly important, but we thought that the EVA experience was really the whole point of going there.
But I think it's important to point out we have other robotic assets that we talked about using, and we would use our judgment. For example, if there were parts of the asteroid that we could anchor to, then the SCV would be anchored there. The crew would be attached to the SCV. We could deploy the drilling and seismic equipment without stirring up dust. If there were other areas that were particularly dusty and interesting, we could use a different combination of assets. And so the key thing, as John pointed out, was to really use the humans for what they're best at, but certainly some judgment goes along with that. If it turns out the whole thing, you're just stirring up dust, you probably don't want to do that.
Hi, I'm Dan Shears from University of Colorado. I think it's really exciting, the things that you're talking about, and I can't wait till something like this happens. One thing I have a slight worry about is that you seem to make a lot of assumptions about your ability to couple with the surface of the asteroid. And this is an aspect of asteroids, especially the smaller guys that we would probably go to, that we really don't understand. And I just think it would be good to have, or to try to relax that assumption in the work that you do and see if there are solutions, which I think there are, that wouldn't necessarily rely on the ability to couple strongly to the surface of a small guy like this.
And we did have a lot of discussion about that, and we said it would be preferable if we could. Having said that, the fallback plan that we think would work on almost any asteroid would be to station keep in the exploration vehicle and then have an arm that would position the astronaut. And then, much the same way we do spacewalks on space station, you could move the astronaut around to do the various sample collection and instrument deploys. And so that would be the fallback plan, and that's an integral part of the capability.
And one of the reasons why we'd want to attach is so that we wouldn't have to carry as much propellant for the free flying, for the translations and station keeping aspects. So it would help the architecture in general if we could dock to it.
Right. The amounts of delta V you need to hover aren't that big, but okay, thanks.
Dan Britt, University of Central Florida. Just an observation about sampling and processing and doing science on sample on the way back. Number one, from a safety point of view, I think the last thing you really want to do is have the crew handling the samples coming back unless you have a fairly elaborate glove box system, which would be kind of heavy and expensive. And if you drop the glove box, you'd have plenty of fuel for hovering then. Plenty more mass for fuel. The other thing is your high precision sample team back on Earth. The last thing they want to do is have people handling that sample before they get to it, because you're changing the environment and the chemical environment enormously when you bring that sample off of a highly oxygen-starved asteroid surface and bring it into an oxygen-poisoned, water-saturated capsule with a bunch of sweaty humans. And unless you have a really elaborate glove box system, you're gonna have problems.
Well, actually, the glove box system is one of the things that we would want to have, and the bottom line is, it's true you don't want to handle all of the samples, but it's also true that we only have certain capabilities to return the samples to the surface of the Earth, and so you'd want to be able to triage with the scientist on Earth as you're going back, returning to the Earth, to figure out what samples are the best ones to bring back.
If I had a choice between triaging a bunch of samples in a 50-kilo glove box, I'd say dump the glove box out, take 50 kilos of samples.
So we had a lot of discussion here, and that's interesting input, and we're wide open to the right way to do it. But the thought was, it's certainly not good use of crew time while you're only there for 2 weeks to do all this high grading, and the thought was, if we could grab a whole bunch of samples. And we talked about everything from glove boxes to actually a nitrogen pressurized inflatable area with cameras and so forth. And the thought was to use that long trip home to really work with the science team on the ground to figure out the ones to bring home.
Yeah, but you're not going to be able to haul the ion probe with you. And that's what the science team on the ground is going to want to do. Well, the other thing is that this object is much more likely to be monomineralic. That is, that you're going to have a single compositional type.
Okay, next in the back.
Yes, Jim Dunstan. Actually, this is kind of a follow-on to that question. Was there any notional concept of how much you would be bringing back in terms of sample? Are we talking about an Apollo-type sample, or are you really talking about lopping off a big chunk and bringing it back and studying that along the way, just in terms of maybe even a percentage of inbound mass of the whole system?
Well, we talked about a wide range, and all these are just ideas, but one thought is if we had 2 very small Earth return vehicles, each one would be capable of bringing the crew back. But all the living and exercise and EVA robotics, all that's in the space exploration vehicle. And we have these redundant Earth return vehicles, and if they both work, we could load one of them full of samples, and instead of giving you 100 pounds or something small like that, there's the potential to bring quite a bit more back.
I think we'd look to the science community to advise us on what the right quantity of samples to bring back was, and I'm sure Clive Neal has some opinion about that.
Yes, I do. With regard, if we look back to the lunar activities that went on, initially we heard that 100 kilos had been allotted for sample mass, and that's total mass, including boxes and everything else. So the curation and analysis planning team for extraterrestrial materials did a study to look at the amount of mass that would be required to address the science goals, and it came out to be substantially more than that. And I would urge that in the planning for this, that samples don't just get an arbitrary number of 100 kilos to bring back, because it's the samples that are going to feed science way into the future. Now, for ESMD, that may not be a big driver, but it's going to tell you an awful lot about your NEO, and also about it's going to add a lot of credibility or more status to the remotely sensed data, because now you have ground truth. Yes, we've got meteorites, but now you have actual ground truth from objects in that space weathering environment that is going to affect the remotely sensed data. So the more samples you can bring, you have to maximize the sample return. And I think that these options need to be weighed very carefully rather than just given an arbitrary mass for which may not be adequate.
Is it always that more is better, or?
It's always. But there are ways to approach how much more and to quantify that. And I think that this needs to be passed off maybe to Captain, maybe I don't know, but to a sample handling group that can look at this and bring in the expertise that's needed to address this question right up front. So the mistake that was made with the lunar launch vehicle or the return vehicle is not made here.
Do you have any thoughts on the utility and or the specifics of how you might high-grade samples on the way back?
Again, a lot of work was done with the moon about having the habitat and lab in the HAB, and what you would do. And there was never really a consensus among the community, but simple is better. You think of doing field geology on Earth. You high grade your samples when you're going over a terrain. Simple is better. It depends, what are your science objective? What are you trying to do with the samples? What are you trying to prove? And until we address that question, you know what type of sample to bring back, then it starts to give you a way forward. So again, my opinion is that you can do it very simply, but we got to learn from Apollo now. There was a rusty rock that came back because it was exposed to the atmosphere of the return vehicle, and it caused changes. And this does happen. It was done in Apollo, and Dan's right that we don't want to expose them to a crew vehicle atmosphere.
Chris, did you have a follow-up to that, or is it a different question?
No, this is a follow-up. Okay. So Clive is actually on a very important track here. This discussion is an architectural nature discussion. If you don't want to get in the same boat that Constellation got into, you have to have made some assessment and decisions about the amount of mass you're bringing back all the way to Earth very early in the architecture stage. Because if you don't, you're limited by the physics of the return vehicle itself. That's what Orion got itself into. It had nothing to do with what we wanted to do with the samples. It had everything to do with how much mass they could afford to bring back under parachutes. So you've got to make these decisions very early in the architecture. Mike was going in the right direction too. If you want to have 2 return vehicles so you get a lot of return mass, that's fine, but it completely changes every other element of your architecture so you can push that huge chunk of stuff all the way out there and back again.
I guess another off-the-wall thought is if you could aero capture and leave some samples in LEO, that if you ever wanted to go back, you could get there and look at them more.
Okay, Peter.
So just a ConOps and architecture-related consideration I wanted to throw in was that, there are several things that we think about wanting there that are quite massive and in some sense also just nice to have. The glove box, certain types of drilling, perhaps something in the nature of ISRU or a mass driver. That doesn't necessarily have to go in the same spacecraft as the crew. And if you had a concept in your precursor mission to have some kind of pre-positioning, you might be able to use a solar electric propulsion to take it and have it there ready. And if it didn't work, it's no great loss. But then you have that solar electric propulsion tug there that could then take back samples and returns and might in fact have its own little aero capture or return to atmosphere, or perhaps you could just leave it in LEO for the space station to look at. But the idea of pre-positioning and a separate trip back from the crew, I think is worth consideration.
Yeah, that's an interesting thought, and certainly parallels some of the constellation with the cargo landers and things of that nature.
Yeah, that's good forward work topic.
Right. What you're talking about there is a form of neo-orbit rendezvous mission, where even though the crew part of it all comes out on one big tug, you have something pre-positioned. So your OpsCon is that you're primarily putting the big stuff together in low Earth orbit and heading out with the crew, but you're pre-positioning something at NEO and doing essentially a NEO rendezvous. So it's a sort of a combination mission. It's not a bad idea.
Affirmative. Last one, Dallas, you got a lightning round.
Yeah, back to the mass quantity. Always, I believe more is better, but going back to Apollo, how much did we bring back? How much did we actually assess, and how much have we distributed out of what we brought back 40 years later?
That's a great question.
I'm sure there's someone in this room who knows that, and Eileen is coming to the microphone.
We have quite a few samples brought back from Apollo, and all of the samples have been characterized in one level or another. The real issue is being able to find the right set and the right portions of a sample within any return. And so we still have on the order of 300 samples allocated every year, 40 years hence. And so you do have long-term value of any of the samples you bring back. And there is nothing that was brought back from Apollo that was not priceless and highly scientifically satisfying. There are some subsets that are more valuable than others depending upon which portion of science, the scientific field you're interested in. And so saying that you don't need to bring samples back or that you want to arbitrarily limit the amount of sample because we have not used up all the 800 kilograms we brought back from Apollo is not a scientifically valuable discussion to have without having representatives from a wide diversity of disciplines aiding that discussion.
Okay, thank you very much. Round of applause for the ConOps group. Good stuff. Next up, we have the Planetary Defense subgroup led by Lindley Johnson and his team. And so, Lindley, you can come on up to the podium and we'll dive right into it. And following Lindley's and the open 15-minute discussion period, we'll have a break after that and come into the final two.
Okay, well, first of all, I want to start off by thanking both my two facilitators, Bill Ayler and Pete Gerritsen, did a wonderful job, and the two scribes for the panel, Stratus Katakulis, and if I didn't pronounce that right, that's the way it ought to be pronounced because that's a fantastic name, and and Barry Epstein. I'd especially like to thank my facilitators because the first thing they had to help me do was put down a near mutiny because our breakout session really wanted to talk about the precursor missions because we see a lot of benefit in the precursor missions. So in order to prevent a hostile takeover of Jay Jenkins' breakout group, we came up with this slide here to make a strong statement here that we really see a lot of synergy between the Planetary Defense Mission and the human mission in the search, survey, and characterization of the NEOs during the precursor missions. And if nothing else, this may be the most important benefit to the Planetary Defense Mission is the work that's done by the precursor missions, hopefully for both human exploration and planetary defense. So after we got that behind us, we then went into two segments of our discussions, and the first one was to talk about what overarching insights and activities would be important to planetary defense during the human mission to an NEO to help further flesh out some of the objectives for the human mission. So at the top of our list, of course, is testing to help add detail and understanding of various planetary defense capabilities. Of course, the human there can do a lot of things with the test equipment. First of all, to make it work if there's a failure, it's not working right, but also to use the equipment in various different ways, some of which may have not have been thought of before getting to the NEO itself. So we see a lot of benefit there. So that kind of goes along with the ability to reduce the risk and failures, so risk mitigation of planetary defense testing. I think there's a lot of lessons that can be learned from the Hubble repair missions and the type of improvisation that was done during those missions for work at the NEO. Last bullet is along those same lines, the ability for the human crew to synthesize and adapt based on what they observe and experience in their initial days at the NEO. We see the mission and the endeavor to go to an NEO as a great confidence builder for a campaign of operations for planetary defense. We will gain a lot of knowledge, expertise, and experience in such an endeavor. The testing that can be done at the NEO will do a lot to increase our confidence of some of the proposed planetary defense techniques and capabilities. For instance, impact effects, the so-called beta factor that I don't want to go into the technical detail of that, but there are certainly unknowns that we'd like to understand a lot better before we actually have to conduct a real-world planetary defense mitigation activity. Some of these techniques do require attaching things to the surface, so testing and experimentation with surface attachment concepts and equipment would be an important activity. Precise anchoring, placement of things like explosives or disruptors, how that would be done, and to test how it would be done in a real situation, whether it be by humans, which we find kind of doubtful, but just testing of the techniques that then later be used by robotic spacecraft. You're just starting to see here that there's actually a lot of overlap and redundancy with what you've seen with some of the other groups in talking about surface activities, anchoring of things, attachment, surface operations. Here's another one, testing of autonomous terrain relative navigation systems, either for use in a gravity tractor or something that might need to be landed on the object for the mitigation technique. Also testing of ways to rapidly develop the gravity model, testing of different modeling techniques to be able to get the gravity model in a matter of hours, if at all possible. Don't know exactly how that'll be done, but it'd be great if it could be. Then in looking at areas of engaging the public awareness, keeping the public base and support to these endeavors, a mission to an NEO would certainly increase the public visibility of the whole enterprise and aid in their understanding of what these NEOs are and why they can present a threat to the Earth, an impact hazard to the Earth. So being able to sustain human interest during an NEO mission there might be an advantage there to doing just robotic testing of planetary defense techniques and activities. The additional interest brought in by humans at the NEO could be a benefit to the planetary defense mission. And then, of course, international participation, having it be an international mission with an international crew, helps to build confidence in the type of international decision-making that's going to have to take place should we get into a actual mitigation scenario where it might, we're still working with the international community as to how decision-making might be done and sorted out, but it's obviously got to be a multi-nation effort to decide if the Earth is going to be impacted by an object, who's going to do what, when, to mitigate that. And there are certainly discussions within the United Nations, particularly in the Committee on Peaceful Uses of Outer Space, on that kind of regime and protocol. So we see benefits from this activity, mission activity, to help us out in those areas. Okay, and then we went into looking at specifically what tools the human crew might take with them, tools or techniques that the human crew might take with them to test specific mitigation techniques. And we have a whole list of those things that are roughly divided into two major categories: either something that is a rapid impulse, give a punch to the object to change its velocity vector enough so that it is deflected from an Earth impact trajectory. So the first one of those, and these are not in priority order or in order of what we think is feasible or not, or would be most effectively, but just to get them on the deck here. First one we talked about is a surface explosive, just a conventional explosive on the surface to give it a little bit of a push. And so you need to look at attachment techniques, how that device would be anchored to the surface, and then what kind of explosive devices might be used and most effective. Now, I have to caveat all this by saying our breakout group were not experts in crew safety for the mission, so we didn't try to do any kind of dividing out here as far as what a crew might be allowed to do or want to do. Just things that might provide important and significant information to these mitigation techniques. Another technique is a subsurface explosive that actually blows off a considerable amount of material from the object to effect a course change, or if it's a small enough object and it's a big enough explosive, it completely would disrupt it. There are advantages and disadvantages to that technique, but it is a technique that is discussed. So looking at penetrators, some kind of penetration gun, seismometers to understand the structure of the object, so you know what are the best places to put the explosives, for instance, to better disrupt the object. Things as simple as digging a hole. What does it really take to do that, and keep it open to put explosives into. Drilling. You've already seen a lot of talk about drilling devices and how to anchor and operate them. And again, small explosives to get those effects. Okay, some of the other leading candidates for mitigation techniques, the kinetic energy impactor is certainly a big one, since you've already seen one work, at least to impact a small body. Whether it really would do the velocity change or not, theoretically it certainly makes good sense, but might want to do some testing of that. So use of a hypervelocity gun to get a little better idea of what the effects might be. And again, measuring this beta factor, that's when you impact one of these objects, it causes ejecta to come off, and the beta factor is how much that ejecta multiplies the overall force of just the impactor. That's what the beta factor is. So there's an unknown. That may be only 1, or it may be as much as 10 times. Finding out what the variation of that is for various types of objects is an important thing. Again, seismic measurements, Measurement of mass is always an important thing. That's one of the most important things we've got to know with mitigation technique is what kind of, how much mass are we dealing with. And then there's the one that we don't hope we never have to use, but if we get into a near-term impact threat, and it's particularly if it's large, a nuclear device or a physics device, as I like to euphemistically call it, it would be maybe our last-ditch capability. So measurement of the surface characteristics, again, how that works is you blow off a lot of material, causing a deflection. So measuring all those characteristics of the surface down to about 1/2 meter is important in measurement of the mass. Okay, let's go on to some of the slow push techniques. Got about 3 or 4 of these. Ablation techniques, again, the idea is to use something to blow off mass, to change the vector. So using a laser to do that is one of the ideas. So small use of a laser to show ablation and how it works, how much mass, and measuring how much mass might be taken off is a good experiment. Using a mirror to focus sunlight, seeing what the effect is of that, and then measurement of how much, as I said, how much mass is taken off and what the velocity of that ejecta caused by those things. Enhanced natural effects, these are the ideas of you let the sun, solar energy, really do the work for you. If you change the surface of the object, it's albedo. So changing how much the object, solar energy the object absorbs versus what it reflects, that over time can have a significant effect on the object's orbit, particularly if it's a small object. So we might have do a campaign here of you get good measurements of the albedo before you get to the object, and then perhaps at the end of the mission, the crew does something to change that on the surface of the object. It could be something as simple as just scuffing it up with your boots, or take some garden tools along and just rake the surface of the object to change the brightness of the object. Rock garden. This brings a whole new concept to rock gardens, doesn't it? And then after the mission, after the crew has left, you continue to track the object after the mission to see what the effect is. Gravity tractor, placement of precision transponder, precision LiDAR and radar, testing of those techniques, and then autonomous operations and navigation for something that might actually be a robotic device when you get to an actual scenario. Attaching thrusters, we don't think this is a real viable concept because a rotating object, you couldn't have continuous thrust. But attachment of devices, things like a large solar cell or something, attitude control of those devices, and then also what the effect of the dust environment that might be kicked up would be. And lastly, one we think is probably the most, at least unknown, if not effective, is things about mass driver. Okay, with that, we also wanted to do the operations concept job for him. And I don't know if you can see this very well, but Peter is excellent at putting together ops concepts, so he's got a little cartoon here he'd like to talk through for about, what do you got, 3 minutes?
All right, so it's always difficult to be the one military pilot in a room full of rocket scientists, so I have to try to reduce it to simple stick figures that my mind can understand. But actually, in terms of trying to look at what would be a synergistic ConOps as it relates to planetary defense, this is kind of how it would look. On the left side, you have a telescope that looks for that becomes the survey, but you're looking for targets. That has great synergies because in terms of the actual planetary defense, that's a huge takeaway. That, of course, establishes the target. Then the next phase is to send a precursor mission which captures the morphology, the spectroscopy, gives you an idea of the surface characteristics, and perhaps also another precursor that prepositions some amount of equipment. At the end of that, you have a well-characterized, what does it look like, something you could post on Google Earth, something that people could get a sense. The next phase, the manned portion of the mission come. At the top, you can see they instrument it out, they drill core samples, they put the reflector or the transponder there. And the conclusion of that phase, now you see the next. You have a good idea of the interior structure, the micro porosity of it, what its internal structure looks like. Then you have the crew start to look at tools. So they look at the potential mitigation options, and I've sort of drawn out here. You bury an explosive. You have light concentrated to do some boiling off gassing. You have your ship try to orbit it at one radius to see if your autonomous gravity tractor software works and if you can detect a change. If you've got the technology and it's not, you might try something with a mass driver or a hypervelocity pellet. And then at the conclusion of that, you move away to a distance that if there is a distance that it's safe for something more dangerous. Now you attempt to take a look and observe an impactor. An impactor comes, throws off the ejecta, makes the crater. Then you either telerobotically or with your people go back, try to get deeper core samples, leave behind, again, a fully instrumented asteroid that can be tracked. And of course, you take your samples home in your either in your spacecraft or in the precursor prepositioning thing that came there. Now, what is the synergistic takeaways for planetary defense of having stepped through this? Well, you complete the 140-meter congressionally tasked survey, or down to 140 meters. If you've done the precursor mission right, you have an off-the-shelf advanced recon probe or tagger tracker that you could actually pull off the shelf toward any real threat. If you've actually done the impactor, then you have an off-the-shelf interceptor. You have at least one tested tool for a kinetic impact that you can throw against, that you say, I've taken this to a usable TRL. And then that same impactor, if you construct it in such a way that the seeker guidance, fusing, casing, and everything would allow for an explosive internal package, you've done most of the work to get you to a second capability that you could throw it against. Then you've characterized a significant amount of information for planetary defense mission planning in terms of orbital deflection, orbital dynamics and planning, modeling for mitigation techniques in the kinetic impact, surface, subsurface, explosive, gravity tractor, and light ablation. You've advanced those in TRL and workability and your confidence in those. And so you've in effect gotten yourself two tools that you can actually apply, plus the survey and the potential mission stuff. There was one thing that I thought I would bring up, is that if you're actually thinking about trying to move an object, particularly one that is on a potentially hazardous list, there are going to be a lot of people that are going to ask, well, is it possible you're making the problem worse? So in that case, I think the easiest case, if you could find it, would be to do that on a totally interior object, where you could very easily explain to the public that this is inside the orbit of the Earth. Anything we do to it is just going to move it closer to the sun. So there's no problem with that.
Okay, thank you very much. In the interest of time, we will open it up for questions. However, we'll have a shorter session, so we'll look for 10 minutes or so of questions. Go ahead.
Tethered satellite was a great example of a demonstration of linear momentum exchange using tethers. Did you guys look at the possibility of using tethers and then cutting the tether?
Well, that idea has come up in discussions with planetary defense. We did not discuss it here today. It has been talked about, though, and we've had planetary defense conferences, 3 of them now over the years, and it's been talked about there, but it was not talked about today. What you wanted to add?
No, I was going to say that.
Okay, you might wait. It proved to be very efficient on tethered satellites, so it might be something worth looking at.
Okay, good. There are some papers that are published on that topic, so that would be something we could use for reference, right?
Okay.
Clark.
Yeah, Clark Chapman, Southwest Research Institute. And this is mostly about Lindley's presentation rather than Peter's. It struck me, although you have a long list of deflection techniques that have indeed been discussed, I think most of the analyses have kind of centered on 3, and it seems to me that they're kind of disjoint in the following sense. Kinetic impactor, for sure, we'd like to determine beta, but when you have a rendezvous mission with human beings there, I mean, you've got 0 delta V, and it just seems like kind of the wrong kind of mission to be testing the explosive reaction. Now you can, if you want to bring explosives or hypervelocity guns along in a spacecraft, which I'm not so sure about, but I'm not an engineer. You're nonetheless operating on the body at a very much smaller scale than what you would do in reality. Another one is the gravity tractor, and that, of course, is a device that doesn't really care about what the surface is like. It's just the relative mass of the spacecraft and the asteroid. And the third one, the nuclear device, is one that's really applicable to NEOs that are at least half a kilometer, maybe a kilometer in size and larger, so the kind of body we're likely to visit is much, much smaller and may not be representative at all of the response of the larger body that you'd use a nuclear device on.
Yep, yeah, copy all that, but we understand that, or at least a lot of us do that are talking about it. But I think regardless of the size object we go to and the effect that's used, that there certainly are useful things that could be tested by a human crew.
Yeah, and by the way, just to add to that, on the kinetic impact, the idea was to do some kind of a survey around the object on different types of surfaces, so we could get some feel for how it varies over an object, for example. And we did throw in a hypervelocity gun. We'll leave that to the designers to figure out how to do that. But so yes, indeed. Same on some of the other topics, to really get a feel for how the surface varies around the object.
One of your slides called for determining the gravitational field quickly. This is normally done, my name is Dave Beatty, Mars Program Office. This is normally done by putting an object into orbit around a planetary body and tracking its position very precisely, or by carrying a gravimeter across the surface and making surface measurements. I don't see that either of those is a particularly quick way of doing it. Were you thinking of those two, or did you have some other way of making that measurement in mind?
We don't have a technique or solution in mind. It would just be nice if we were able to do that quicker.
Right. Yeah, I mean, maybe one approach you might consider is this is a small body, so maybe you can use multiple small orbiters to do that quicker, or small bodies that have it ejected or something like that. Again, we didn't know, but the idea of being able to deal with that problem early would be good.
The idea, though, is the human crew could test, 2 or 3 different techniques.
I just wanted to ask a question on operational approach to an actual interception of a near-Earth object that we're worried about. Most of these and excuse my ignorance on it, I haven't been a part of any of these discussions before, but these techniques seem to imply that you know that this is coming a long time ahead of time. I know you're talking about testing out these techniques on a human mission, but in an actual operational scenario, you have to detect this near-Earth object and know its immediate risk to the Earth, right? And so that means to employ some of these techniques, you need to know about that a long time ahead of time, be able to get the orbital scenario or orbital mechanics worked out so that you can actually get a spacecraft there to apply one of these techniques. So is that the general assumption, that you have to detect this a long time ahead of time? Or?
The most important component of planetary defense is find them early, find them early, find them early.
So you don't, would you have techniques, though, that you would think about for interception for more immediate immediate detection?
Probably have to resort to the nuclear standoff.
No, a quick comment about the gravity field determination and the orbiting. It's very difficult to orbit the small guys, and the reason is the gravity is so small that your solar perturbations dominate. And in fact, the threshold at which it may be not possible to orbit at all is more or less the region where we are. And that if you choose to go to a target that's, say, at least the size of Itokawa or something like that, yes, you can still orbit. But then you need to orbit for at least several times before you have any chance to infer a gravity field. If you're talking about a 50-meter object, it's not clear you can orbit at all, ever.
I hate to belabor the point, but we've done some analysis recently and presented it at the aspects of it at the last 2 spaceflight mechanics conferences, and you actually don't need to orbit a small body in order to get the gravity field. You can get the gravity field by a number of relatively slow hyperbolic flybys, where your V infinity is on the order of centimeters per second. And that actually is a pretty effective way of measuring the gravity if you get the right latitudes for your flyby trajectory. And we have some papers on that if you're interested.
Great, yeah. Sure.
I just want to mention that one of the reasons why we're interested in the gravity field is some of the techniques we've talked about either require a landing, which means you need to get there, or secondly, require flying in, basically maintaining a station with an object that's rotating, and sometimes maintaining that station very closely. So one possibility, of course, would be to develop a system that automatically does that in a fuel-efficient way. So again, the task is what I said. You need to be able to land something and maybe attach and so forth, and so you need to make sure you know enough to do that. Or secondly, if you need to do either orbiting or station keeping, you'll need to know enough to do that well and potentially stay very close.
Yeah, and it may not be done by the spacecraft orbiting the object. It may just be from the spacecraft standing off and the object rotating underneath it that you sample the gravity field.
Is this live? I think we're making a problem where there is none. The gravity field of these things is negligible. You're operating around it like you would with the space station. If you want to land, you actually need to fire your rocket motor the other way and force yourself down onto it. And its own gravity for a 50 or 100-meter object is completely negligible.
I don't think it's so much for landing as it is for maintaining the station keeping for a gravity tractor.
Yeah, but it does that by a LiDAR sensing its distance from it, and again, the actual gravity field is extremely small.
Okay.
Final question. It's Jürgen Schlutz from DLR. I just wanted to maybe take this a little bit off topic towards both from the human missions and towards the precursor missions again. You were already mentioning that one of the biggest aspects is finding them early. Another aspect is knowing as much as we can about them. Is there, or when we were talking still about lunar missions, there was a strong interest in characterization of globally of the lunar surface, in sending nodes to different destinations and get a net of measurements like the ILN network, for example. Is there a similar approach, or has there been, to defining a characteristic payload that we want to send basically to every NEO that to enable comparative analysis of different objects?
Well, we didn't specifically talk about what the components of such a package might be. It's certainly an idea that's been talked about in planetary defense discussions. But building up a catalog of characteristics for different types of asteroids so that whenever we are eventually faced with such an object, we already have a lot of knowledge about that type of object so that we don't necessarily have to do a full characterization mission against it before we would do a mitigation campaign.
Okay, ladies and gentlemen, we are, thank you very much. That was another excellent panel. We are now on break. We will resume at 3 o'clock, 1500 sharp. And following the break, the two sessions will be Chris Colbert leading the synergies with Moon and Mars, and Gail Allen leading the policy. So see you back at 3 o'clock sharp. Hey, Lindley, one thing that I was